Welcome everyone to this workshop. Can you hear me well? Someone? Yes, good. Please let me know. If not, then I will need to change something maybe with my network also. But for now, it looks good. This AI for You experiments workshop about streaming. This is something that we did not foresee in the beginning, but we found out during the project that this is a need. And so we implemented part of it. And today we will see what are the possibilities. So what is the agenda? I will explain what is streaming in theory, what are patterns of using streaming. Then there will be from Joao or from Duarte the YOLO pipeline demo. Then I will also show how the YOLO pipeline looks in practice in Akumos. Then I will talk about one important ingredient of that pipeline, the custom collator, why we needed, how to implement it. There is also a link to a Git repo, so you can also all look at it and change it for your own purposes. Then I will talk about subcomponents, how to use streaming for calling subcomponents, how to access solvers in general. Actually, the solver patterns, they will come after the last point. Anyway, I will show the Sudoku streaming example, which uses subcomponents, how it differs from the Sudoku non-streaming example. And I will also show the AI for industry in action, just as an example. And then Uwe and Alessandro, or maybe only Uwe, will talk about their use case. And yes, in the end, I will talk about the solver patterns. We continue with streaming, theory, and patterns. So what can we do with streaming? In general, we can do event-based communication. This is just another name for streaming here. It means, for example, a camera can stream out images and other components process them. We provide data not in one piece, but in many pieces, like events, in a stream of data fragments, in a stream of messages. Another example, user interfaces can stream out user events and stream in the results for the displaying. We can have multiple remote procedure calls with different types that stream out messages, and we can have multiple remote procedure calls with different types that can stream in messages. And each of these remote procedure calls can have a different frequency. And usually we implement this in a multi-threaded server that has queues. So each RPC is talking to a queue, either reading from the queue and sending it out, or reading from the RPC and putting it into a queue. And then we have one central thread that combines all the data, works on all the data, and does what we actually want to do. This is how we technically can do this, that one component has multiple interfaces to plug in and send in and receive out messages with multiple remote procedure calls. You will find code examples in links in this presentation. I will also share the presentation later in the next cloud. Next point, control loops become possible, which means we have components that are organized in a loop. It's like a user interface, only it's more a pattern. The type of component is simulator or environment, sensor, controller, actuator, and then this goes back into the environment or into the robot that modifies the environment. If it is a pure software solution, it's a simulator that simulates the robot and the environment. These control loops become possible with streams because we can have a different frequency of sensor information, controller, actuation information, and this can be in a loop that continuously sends messages, not once, continuously. And next point, components can use other components as subcomponents. This is not about continuous. this is about to stream out whenever we need one request to the subcomponent and stream in the one result from the subcomponent. It's possible that subcomponents provide multiple results, of course, but the basic case is we have another component attached to our component. We want to send one request and get a response. And maybe an hour later, we want to send another response and one request and want to get a response. The final point, it is possible to integrate ROS with this because we can see streaming out as publishing to a topic and streaming in as subscribing to a topic. And then we don't have any blocking issues, or it's possible to build this. It's not automatic, it's not for free, but it's possible. It's not possible without streaming. So what is the technicalities? We now support the stream keyword in the protobuf interface of the components. So for your experiments, every component has a protobuf interface, and the stream keyword is now supported for input and output. And if you have multiple components and you connect them in the design studio in Acomos, you can connect streaming and non-streaming ports. And this is handled transparently. So how does it work that it is being executed, this solution? First of all the components are started up. And then the orchestrator, which is an additional component that is automatically added to the solution, connects to all these components. And between each two ports, an output and an input, there is a queue. And this queue holds the messages. So if one component creates output in a very fast way and the other component processes them slowly, this queue can grow, or we can say the queue has a fixed size, then the queue does not grow, then messages get discarded. And every remote procedure call is handled in a thread. And if there is a message in the input queue, or if the input message is the empty message, this is written below here, if the input message is the empty message, or if there is a message in the queue for the input, the remote procedure call is started and the message is put into the remote procedure call. And then the remote procedure call can process and create output. And this will then trigger other remote procedure calls that are connected to this output to become activated. The orchestrator source code is also available. And there is also the possibility to write manual orchestrators for testing, for local testing. If you don't want to deal with Kubernetes for developing, if you say, I run it in Docker or I run it locally without Docker, you can do this. There are orchestrators also online available, 91 lines of code here for Sudoku. And it's possible to write an orchestrator without multi-threading, just because you know how the topology looks like. The generic orchestrator is a bit more complicated because it needs to process the files that come out of the AI for Your Experiments platform. And it needs to deal with Kubernetes to some extent. So, yes. By the way, you can also interrupt me at any time and ask questions. I see the list of participants. So if you want to raise your hands there, I could also see it. Now, more concretely, how can a component send events to component B? Or this is one of the use cases. A component can stream events to another component. We have a component with an output port. In Acomos, output ports are black, filled black, and input ports are white. And they don't have written stream output or stream input, but I write it now for you. And this output port can be a stream output, and the event is the message type. For example, an image goes into the next component. This component A will have the following interface: RPC, some name, empty, returning stream event. For example, this component can be a data broker, and the event is a data set to process. Or the component is a user interface, and the event is the data submitted in a form by the user. And whenever the user clicks submit, the form is packaged into the message, is sent out as a stream, and the orchestration will run the rest of the pipeline, run the rest of the solution to process what the user submitted in the form. And then the result, we will see on the next slides, will be streamed back to display it. Empty here is a special name. If you use this name, then you also need to declare the empty message with an empty body. The important thing is here that our parser in Acomos does not support if you put the braces directly next to each other. You need to put it into the next line, the closing brace. So maybe I should make this here as a new slide. So this is what I want to say. This will work. Everything else will fail. Sorry for that. I tried to fix it. It is very complicated to fix it because the parser is not a parser. The parser is an ad hoc code. So I decided to throw an exception if something arrives that I know that is unparsable. So this is how you need to declare the empty message. If not, you will encounter errors. A week ago, you would not encounter an error and it would not work and it would not be debuggable. So we have improved the system a bit. This is the empty message. The empty message just means, okay, you can create the message and start the RPC call immediately. This is necessary to start a solution that has a cycle, for example, because a cycle needs to start somewhere with processing. Some RPC needs to start to produce output, otherwise a cycle will never become active. So the component B here is the start of a pipeline or application. So either this component streams in events and streams out results, then the component can decide whether to ignore some events or whether to produce multiple results for one input event. The process can also be without a stream for the output. Then the RPC will collect a few events or no event and return a result. And then the orchestrator will restart the RPC. There is a third possibility. If there is no stream keyword at all, then each event will be processed by an RPC, create one result, and then the next RPC will be started for the next event. Actually, this is missing on the slide. I will also add this, if someone wants to use this as a reference. It will need to be more clear on that. Yes, how to declare the empty message. Another possibility with streaming topologies can be cyclic. For example, we can have the thing here below, the simulator and the controller. The simulator creates streaming output sensor data. The controller has an input and an output. The actuations go back to a streaming input in the simulator. Here we again see empty. The simulator output starts without any input to create sensor data. Then we have a symmetric simulator input with a stream in and an empty output, which means it doesn't make sense to connect anything to the output of this. This is just meant to stream in actuations into the component. And the component either displays them or has some other way to stream out a corresponding result. In this case, the simulator will, of course, internally have a connection between these two RPCs. The controller, for example, could say, like before, one input, one output. Then for each sensor input, we create one actuation signal, or we have a stream for input and a stream for output. probably this is the more likely scenario. So we observe sensor inputs and only sometimes provide actuation signals. Or we always provide actuation signals even if we don't receive sensor data for a while. This is also possible to do. So with streaming, we have a lot of freedom over the factor of time in the solution and how many messages we produce as output for how many input messages. Now there is one caveat. You cannot make a cycle by just creating two functions, input, output, output, input, and connecting them. This will not work because there is no empty message anywhere. So none of the RPCs will be started initially. The orchestrator will not initiate this cycle. Also, if you have streaming input, streaming output, this does not work in the current implementation because the orchestrator will only start an RPC call if there is an input message or if the input message is empty. So this would correspond to this figure here on the top right. My son just woke up. I need 1 minute to carry him. Be right back. So sorry for that. I am back. The previous slide showed how not to do cycles. This slide shows more or less the main way to do cycles. We have a component that has, if you want to do a cycle between just two components, you have a component that has an RPC call with an empty input and a component with an RPC call with an empty output. And this breaks the cycle. So the empty input initiates the computation. We can see here the 3 remote procedure calls that are necessary. And the component B has some function that has some kind of input and some kind of output. Can be streaming, can be non-streaming, can be streaming only one side. Does not matter. These types of cycles will work. And it's also possible to have multiple layers of cycles with different frequencies. Here I just invented some architecture I tried to write a solution that contains 2 control cycles and a user interface to give goals. So the user interface streams out goal information depending on user action to a planner. The planner streams out low-level control goals. The controller uses the control goals to create actuations. The actuations go to the simulator. The simulator again streams into the user interface to show what's happening in the world. And the simulator streams to the perception module. The perception module creates a symbolic representation of the perception and gives maybe low-level information to the lower-level controller and high-level information to the planner. And this way, there is one control cycle over the controller over perception, over the low-level controller, and one control cycle probably with a much lower frequency over the planner. So this is all possible with streaming. Yes, this is more or less, of course, I have not implemented such a thing. This is just an idea of what is possible. The next point is streaming, viewing streaming as publish subscribe. So a port with an empty input can be seen as a publish. A port with a streaming input and empty output can be seen as subscribe. If we want to call a submodule, we need 2 RPCs in the caller, publish request, subscribe to results. The component that we call the subcomponent, we it doesn't need to know that it will be a subcomponent. It can be any kind of RPC or two RPCs. If we need a controller, we also need two RPCs, probably in the controller and in the world or in the simulator. And if we have a component that has streaming input or streaming output, this provides more flexibility for connecting with other components than if we don't have streaming input or output. Because if we don't have streaming input or streaming output in all components, for sure we cannot make a cycle. Maybe we don't want, but if we want to have a cycle, we need some streaming keywords somewhere. Now we come to the YOLO example, because this brings us to the custom collators, and because we need streaming for custom collators. And now I'm asking Duarte to take over and show us what you created.
Maybe a question, Peter, before we move forward?
Yes, sure.
Something, I mean, maybe obvious, but something we were wondering also with Uwe. In the standard orchestrator or in the streaming orchestrator, is there any way to already, or it has to be implemented, to see what messages are being passed, what RPC calls are made, and so on? So how can we trace or even log the activities of a pipeline?
This exists. Maybe I can just share again. So if you look here in can you see my shell?
Yes.
So here I have this script just runs the orchestrator client of the parallel orchestrator. That's from Akumos. And here I can see all kind of observations. So this script attaches to the observer RPC, which is also a streaming RPC that provides events. And this is the AI for industry example. So if I now click here, you can see there were some events happening. And you see there was a delay because the reasoner needed some time. And yeah, here you can see some details of that. So we call the RPC called compute. We distribute the output message from the RPC compute. We add it to the queue, and the RPC is finished, which is not always the case if something's added to the queue, because streaming output might put more than one event. And here we consume from the queue and call the next RPC, which is display result, and so on. So this is new. This is in the parallel orchestrator, which is the only orchestrator that is remaining, because it can do everything that the original orchestrator could. Or it's supposed to be able to do everything that the original orchestrator could. I recently was notified of some issue with exception codes, because a data provider will tell the end of the data with a special exception, and then our orchestrator client should terminate and say, we are done. But yes, the idea is that this is the universal orchestrator that can do everything, and it has this observation. So if I press Ctrl+C now, the orchestration also continues. So I can change here, click again, submit, and after a while I get the result. Because the orchestrator runs in parallel, what I terminated was just the observation thread. At the moment, the observation is only possible when you run for the first time. If I run again, I restart the orchestration. I cannot reattach. but this is also something that can be added later. For now, what you can do is see the events after you initiated the orchestration. And you can filter for event names. If you have too many events, you can filter them down a bit. And if you modify the code of the orchestrator client, which is in the package that you download from Acomos, then you can even display the content of the events. At the moment, they are not displayed, but they are transmitted. So you receive even the content of each message in the orchestrator client, which can help for debugging.
Great. And this is in the parallel orchestrator, you said, but the streaming one, I mean, streams have been put in the parallel orchestrator, or is it a different orchestrator?
This is the same orchestrator. The parallel orchestrator was created because of streaming. But yeah, it's the same. There is only one.
Thanks. Yep.
And now, Duarte, are you ready? I think you can share your screen. I hope you can.
Okay.
I'm not sure. Maybe someone.
Yes. I can. Okay. Well, I'll share my entire screen because to see the terminal. So for the YOLO pipeline, it is a pipeline for object detection. And so right now it is running with Docker Compose and a custom orchestrator. But yes, I can start it right here for the demo. And okay, I think, oh my God, Zoom. I think it has already started. Okay. I need this IP. And it has just a simple web interface. So sometimes it takes a little bit to generate the first image, but okay, it's not even there yet. This is because everything's running on CPU, so it takes a while. Okay, now I have the stream. And well, this is it. So it is just a camera that goes into a model that predicts the bounding boxes of objects and classifies them like with person or car. And then we have a visualization that receives both the image and the predicted objects and draws this in a web interface. So this is it. I don't know if there are any questions.
Thank you very much. I will now show the background of this, or how we do this in Acomos. Probably I should share my screen. Here you can see the YOLO pipeline in Acomos. You see the YOLO camera. I said before that the output parts are black and the inputs are white. So here you see this is the RPC called get. The output type is image. And this is the RPC called get, and the input type is empty. So this image from the camera, it goes into YOLO and it goes into the custom collator. the output of YOLO, so YOLO here has detect, input is image, detect output is detected objects. And what we want is to show the image and the detected objects in the visualizer. So the visualizer has image with objects type. Okay. I always forget to press Shift. So here you see the thing in protobuf. The YOLO pipeline has the image feed service, get returns image. Actually, it has no stream, but it could use stream. It would be a good use case for stream. The YOLO has detect from image to detected objects. And for each image, there will be one instance of detected objects. Here, it does not make so much sense to add streaming because it's always one-to-one. And we are typically called by someone else who knows how to call us. So streaming here will not give us any real benefit. And the visualization service visualizes an image with objects, and an image with objects consists of an image and the detected objects. Now we want to connect the output of this service and the output of this service with the input of this service. Acomos does not allow this. Well, Acomos allows this with so-called collators. And Acomos has collators, but they have many problematic issues. And we did not make them work. We could not make them work. So at the moment, we built a custom collator for a specific input-output message. And here I show the protobuf interface. It is a streaming input for image, a streaming input for detected object, and a streaming output for combined output. And you can imagine that we can just connect it like this. And here I can show you, this is the collator. It has many fancy ports because it has, for each remote procedure call, it has 2 ports, 1 input, 1 output. But you see, there are 3 empty ones, 2 empty outputs because we have 2 streaming inputs, the images and the detected objects, and 1 empty input because we have a streaming output, image with objects. And there are 2 more ports there for the shared folder mounting. For the shared folder mounting, we don't use this. We only use this if we really need this. If we want this collator to have file access to a shared volume, then we would connect this port. But otherwise, we just leave it open. This is how we can now connect these 2 components to the visualizer. You see that we cannot connect this port to the visualizer. The data type is wrong. And now the full source code and the Docker file to create this is in this repository here. I will just put the source code, the important part of the source code on this slide to show that you don't need to be afraid of this. It is really very simple. We create queues for the inputs. In this case, we have 2 inputs. We create queues of maximum size 1. And for each input, we have, so here we have three RPC implementations, 2 inputs and 1 output. The inputs have the same schema. We go over the input iterator and put it into the queue, here into the queue 0 and here into the queue 1 without blocking. This means if we get too many messages, we just get an exception and we discard the message. This is for these 2 input messages. For the output message, we need to do something different. We are in a loop. We start with an empty input, then we go over the queues and get from each queue 1 input. And then finally, we give as an output the combined message that is assembled from the input of the first queue and the input of the second queue. And The rest of the custom collator is just starting the gRPC server and attaching this class to it. So the rest is just standard code that is always copy and pasted to the next implementation. This is the only specific code for the custom collator.
Peter, can I just one question? So we should onboard each one of us, if we need the custom collator, we should onboard this because I was searching in the experiment.
You would need to modify it for your purpose to add your types, build it, and onboard it. Yes, unfortunately.
No,
At
it's
the
fine.
moment, we don't have a generic collator yet.
Thank you.
This is, yeah. This is a good question, yeah. Practically very relevant. So this is the custom collation, and the next point is subcomponents. What are subcomponents? Well, subcomponents, we know programming is structured because we can structure into subcalls, and we want to structure also our components because this way we can make them more generic and then they are more useful and more used. What is a subcomponent? We have here the component A. I call it the caller. This component has an external interface that we are not interested in at the moment. What we're interested in is if this component needs another component to do its work. It can have a streaming output for requests and a streaming input for responses to call a subcomponent, another component. And this other component B is a submodule of this component in that case, and it just has a standard RPC call without streaming, call, request, response, like the YOLO pipeline. YOLO had this schema of RPC call. YOLO could be used as a subcomponent. And the component A, like before, it has a publish and a subscribe RPC, streaming output, streaming input. And whenever component A requires a computation from component B, it streams out the request, B will compute the response, and then process result gets the response. And how is this actually implemented? So I implemented this in the Sudoku example in the streaming version. And it is just these 2 lines of code in practice. So we, instead of calling the subcomponent B, we put the job into a queue, and then we wait in another queue for the result. And the 2 other RPCs that we have here, like in the custom collator, they take care of the queue. Whenever something comes into the queue, they send it out. And whenever something comes into the RPC input stream, they put it into our receive queue. This source code is also available. And I will also show I will later show the Akumus topology of this and compare it with the one that is not. Yeah, actually, no, there is a reason the slides are in that order, maybe, hopefully. And this way we can also make typical reasoner interactions. So we can have a subcomponent that gets commands from us and we receive the output of the component, like a SAT solver. We can add clauses to a SAT solver, ask for the next satisfying solution, and we might get out a solution. Then we say, we want to constrain it even more. At some point we get out unsat and so on. This is possible. I will give more details for this later. So we don't need to just think in terms of one input, one output. The input can have multiple types by having subfields in the gRPC call. So an example for these subcomponents is the streaming Sudoku. this slide just contains as a reference several links to protobuf definitions, implementations of the server, implementation of the subcomponents, and now I will just go to the solutions. This is the original Sudoku solution without streaming. This middle component has two RPC calls. I just remember that I should show you the slides. This is the middle component. The middle component has one RPC call that prepares an ASP job from the evaluation request, and one component that analyzes the ASP solver response and creates something to display. So this middle component contains in the interface the ASP solver job and the result. So this is not a nice interface. Now, if we have streaming and if we use subcomponents, then the middle component is just one RPC call, evaluation request, evaluation result. And while we compute this evaluation result, we stream out an ASP request on another gRPC call, wait until we get from the solver the result, stream it in, and then we continue computing here. That were the two lines of code that I showed before. Send out to a queue, wait for result on the other queue. And this way, the middle component in the API to the user interface hides the details of the ASP solver. We could implement another middle component that can be connected to the same user interface and uses a SAT solver, not an ASP solver, or uses a Prolog engine, not an ASP solver. With the previous architecture, this is not possible. In this architecture, we have the problem that in the RPC call here, we have the interface of the ASP solver and so on. So now I show it in the AI for Experiments platform. The GUI has an empty input for request evaluation. An output, the output is always on the right side. That's why we have these crosses here. The output request evaluation goes into the design evaluator. Evaluate design. The output goes to the solver job. The solver input, solver output goes back up to process result, goes back into Sudoku design evaluation result, goes back to the user interface. And this is the streaming solution. It has more ports because it has evaluate Sudoku design, evaluate Sudoku design. These two are now one RPC call. We don't connect with RPC call to the bottom. We go down from the GUI and we go directly up back to the GUI. And in parallel, more or less, this component makes a call to the answer set solver down here and gets back the result up here. The important thing here is, which is also very nice, the ASP solver component is exactly the same as in this solution. The ports look different, but that's just how Acumos works. It assigns some symbol to the ports. The data types are the same.
Just one small comment. I think on the development system, the matching models feature should also work. So if you click on one of the ports, then you should see the matching models, maybe.
Yes.
Okay, that's what we learned, you need to click on a port. It doesn't show all the matching models.
I always thought I should click on the node.
Yes.
But no,
it shows per port, and it makes sense if you.
So now I want to do something dangerous. I want to check the mount volume. No, actually, this is not dangerous. Dangerous would be to click on empty. But maybe it will just take a bit of time, or it has been excluded, which would be very clever to exclude empty from the search of matching models. Or I just killed the server process.
Well, it's on the development system. It's the first implementation, so maybe we need to get some feedback to Helge. But I think it's.
Of course, I'll try to break it as soon as I see it.
That makes a good developer. So you can try it out, and it's just the first implementation. So we might need another iteration to get it really running.
Maybe it also, so this is another comment also. This new streaming was added later. Everything that was onboarded before might have difficulties working together with the things that are onboarded afterwards. Especially the orchestrator at the moment has some issues. It expects the streaming features to be set to false. And if they are missing, which is the case for everything onboarded before, it fails. But I will change that. So don't onboard everything again. It's not necessary. It was necessary for debugging, but I will change the orchestrator that it can deal with things that are not aware of the streaming code. And maybe the matching models also works for things that have been onboarded after they have been implemented. Otherwise, it should show more, I think.
Yes, so please give feedback to the matching models feature. It's just the first version, and there are a lot of use cases to take into account.
Peter, I have a question. So you showed both versions, with and without streaming, the same example, Sudoku. So both are online on the Acromos platform. And we can watch, look at them and to see like how to, if we want to use the streaming, and so it's easy to learn, I guess.
The source code is online in the Git repository.
Okay.
One is in the streaming branch. The solution, okay, let me check. The solution, the public solution in the live system I think it is only the non-streaming version.
Okay.
Yes.
Do you think it would be helpful to have both of them online for learning purposes and then to name them appropriately so we know what is what?
Yes, definitely.
Yep. Good. Thank you.
I will put this.
And did you publish the streaming solution on the development system so that other people could see it?
No. It is.
Might also be helpful.
It is here, and there are actually multiple. The same with the YOLO solution. But yeah, I can also publish it on the development system. Actually, if you run the solution, it looks the same. Only the internal structure is better in one case. That is, I also wanted to say this. And I also have I also briefly want to show you see here, this is an orchestrated thing that never stops, because this is the YOLO running on my computer. In Minikube, in parallel to AI for Industry. And yeah, and that is YOLO from Acomos. So I onboarded it privately also in the dev system with the custom collator. And yeah, this is not with, The only issue here is we need to set environment variables of the camera so that we enter the password. Because of course, the password is not onboarded to Acomos. Yeah, this is the only thing that we might need to think about. But it is also simple to edit the YAML file that is created by the Kubernetes client to add the password. But that is a manual step that is required to run the YOLO pipeline, the Acomos YOLO pipeline. So now I need to kill the orchestrator pod because I have not implemented orchestrator stopping yet. And the next point is Alessandro and Uwe with a use case they have that we will discuss.
All right. I think it's a really perfect timing also for this, because I think it really ties in nicely with what you just showed before about the submodules. So our use case, just close this. Yeah, our use case is, I think you have seen this before or something similar, is related to planning and execution on top of a simulator or potentially also a real robot or some other system giving us information about the world. And the idea is that we have something that inputs tasks to the system and then gives tasks to the executor, which would then, based on the current state, it gets from the simulator or from some other sensor system, put together a planning problem, and then sends this problem to a planner, which then generates a plan. And then this plan is executed by, again, sending actions to the simulator or the robot system, and the results of each action are coming back. And then once the task is completely finished, it would send back a result to the user. So in my view, there is another box over here. Can you see my pointer? Just check.
Yes, yes.
Okay, good. So there would be another box over here, which would be a GUI for user, where the user can enter goals and maybe also see the state of the world, or things like this. And the interesting thing with this, in our view, is that it actually contains multiple loops. And this is something similar to discussions we had also with Luca Iocchi, where he had a more real-world example, and there were also multiple loops in there, which was also related to planning and execution. One loop would be this loop of from do task to gen plan to plan and then back to the result. A second loop would be to update the states between the executor and the simulator. And the third loop would be the loop of sending actions and then receiving the results. And I think here, possible submodules could be the simulator of the executor, and in the same way also the planner of the executor, in which we would potentially, and I think here your figure earlier was really nice, because I can see perfectly having inside the executor a module that is responsible for handling this task here. So the corresponding RPC. And then in what we came up, essentially we would continuously ask for new states or receive new states from the simulator. And when we have a plan and it's not currently fully executed, we would stream actions to the simulator or send actions to the simulator. So this is the overall idea. Any questions about that? If not, so the next step we did is actually just created a bunch of interfaces, and then I uploaded a lot of fake components into Acomos without anything behind, but just so that the interfaces would work out, so we could connect things just to see how it would look in Acomos. So we came up with something like this here. So here we have the GUI now as a box, which would send a goal over to the executor, which would then assemble a problem. And then as part of this first loop, then once the problem is assembled, it would push the assembled problem into the planner, which then, is it now here, sends a plan back again to the executor. And now here we would have this, this first loop, which would then be complete. However, once we have received the plan here, we do not go back right away in this very large loop out here, but instead we would first have to execute the plan. And so we would enter into this loop where we just go through all the actions that the planner sends back and ask the simulator to work on them. And then once all the actions are done or we have received a failure, we can give the user feedback back here. And at the same time, the simulator would give us state updates via the getState method down here. One thing I found interesting, actually, that's just a side note, that all of these interfaces here are the same because we kept it very simple. So everything is just strings that are sent around. So we just assume some sort of domain definition language behind that would then could then be parsed by these components, which makes for really bad interfaces. But at this point, there was no.
Yeah, the problem is that this causes Acomos to allow you to connect anything to anything.
Exactly,
and uses the same symbol because the messages have different names, but they have the same content, and Acomos matches on the content of the message and not on the name. That's why
that's also what I gathered from this.
Why you have pink triangles everywhere.
So I think if our interfaces were more refined, this might look better. But then again, if the interfaces are too refined, then we run into problems where, like we had an AI plan for you, where suddenly this interface had to be recursive to support our API, and then this doesn't work currently. So we have to see how to do with that.
Yes, this is another point that we found out in these discussions. Thank you for reminding me. It is possible in protobuf, and it is perfectly legal to have a message type that contains another message type in a repeated field, and this other message type contains the first message type, again in a repeated field. So, of course, this has to end somewhere with an empty repeated field. Unfortunately, the internal representation in Acomos expands this into an endless loop. So I did not see an easy way to fix this in a fast way. So recursive structures, recursive data types, at the moment, we need to do without them.
Yeah, that would be something really nice to address for AI plan for you, because that otherwise we have to somehow artificially limit the depths of the expressions, and that would make things quite difficult on our side. But anyway, this is just a side note. So yeah, so this is currently without streaming. From what I've seen today, streaming should be fairly easy to add, because I guess we just add a bunch of stream keywords. But one question that we actually had is, do you think this could be orchestrated as it is? Or would this run into problems because we have these multiple loops implicitly?
As long as you have for every loop one way that it is initiated, like the user interface starts with an empty input, I think the yellow circles will be empty types. So that's fine.
Okay, so it should work because we have somewhere here.
Yeah, that interface with the mouse over is not so optimal, but yeah. That's
here, for example, do next action has an empty interface, so this would be started. Okay, so
yes.
It would also work without streams, actually.
It would also work without streams, actually, but only with the new orchestrator. As long as your simulator will really create one output for each single input, and your planner creates one output for each input, then you don't need streams in the strict sense. Yeah.
Yeah. So the way we saw streams being utilized here would be instead of having this loop between the simulator and the executor, I think we could just have one stream that the simulator just streams states to the executor whenever it has something interesting to say, let's say. And in the same way, the executor just has a stream of actions to the simulator. And then the simulator might stream action results back.
So the reason that I like streaming is because it makes the Python code much simpler in your component. In the user interface, for example, you don't want to restart the RPC call for each user event. You want to have a loop where you just send out whenever something happens. And this is possible with streaming, or to process something when it comes in. You don't want to be called each time. You need much less state management in your remote procedure calls in Python if you use streaming. That's
yeah.
Just one side note, the new orchestrator is used in all systems now. So there's no system that uses the old serial orchestrators. All systems use the parallel new orchestrator right now.
Sounds good. Okay, so basically then we would even use streams like especially for, let's say, as you say, the GUI to executor loop, because then here, whenever there is a new goal ready, you would just send it to the executor. Then the executor may manage which goals to achieve, or
yes,
may just put works through them whenever it's ready to work through them.
And you could have a separate RPC for displaying stuff and for sending out the next goal, because then you can have different frequencies. You can display continuously what's happening in the simulator, and the user events go out only when the user clicks or whatever you want to have. Yeah.
Okay, yeah, but that sounds really nice. And then I guess to add streams here, we would just have to add the stream keyword to the interfaces in a consistent way. And then
yes, well, does not need to be consistent, but you need to change the code. When you add the stream keyword, you need to change the Python code or the code that implements it.
Which is fine, because for now there is no code behind any of these nodes.
Okay, this is something you can see in the Sudoku repository, where everything is implemented once without and once with streaming. And there you see the real difference, which is not huge, but because it's a simple example.
Okay, and then just to finish this example, because then we're thinking to make this more interesting, it would be nice to have some alternative components, or to spook things up a bit differently, and to show how not so much changes actually in here. So you might have other components over here, for example, a goal manager, which could replace the GUI, or maybe be hooked between the GUI and the. Oh, this is a bit wonky. Okay, good enough. Hey. Okay.
No, they don't stay there where you put them.
So I'm not sure if I can I delete existing connections here?
Yes. Click on the line.
The line. Okay.
Click on the delete button on the upper. Yes, here. This should work. Yes, and then you need to confirm, and then it changes position.
So the idea here was that we might have a mixed initiative planning system, which actually takes care of our planning, which would then also host a graphical user interface. And then we would put this essentially between the planner and the executor, so that then the user would be involved in creating plans. So let's see if I can just create this. Here we assemble the problem, and then we put it over here. And then here we send it back, maybe over here, I hope. So this would be again one loop between those things, but then I think the planner would then be a subcomponent of this thing here.
Yes, that is a subcomponent.
So we go here, and then I'm wondering if I made a mistake here. Wait, it needs a problem.
No, you don't have an output with a pink triangle. You have only orange triangle outputs. There is a mismatch of a type somewhere. I think this query planner should contain a problem and not a solution.
Yeah, there's probably something wrong with the interface, but it's you get the idea. So there should not normally be another thing here that connects this to the planner. I think normally, if you would do mixed initiative planning, you would actually have something a bit more fine-grained than a full planner, but something that exposes like advancing the search space of the planner in a more fine-grained way than just solving the entire problem. And then in the same way, this goal management component right now could just replace the GUI, and then maybe it could also be connected to the simulator, and then the system could create its own goals. And yeah, this would be our use case. Any more questions or comments about this? As I was saying here, we just decided first just to put everything in Acumus and play a bit around with it to see how it actually works out there before absolutely trying to create some code behind all of these things, which would actually turn out to be a bit complicated with all the testing and so on.
I have one question. Do you think it would be possible to replace one of the components with a deep learning module or model?
If there is a purpose for it, then maybe it could be linked to something, but here all the systems are, it could be part of the simulator, maybe, if you have some object recognition in there and then use the deep learning model to extract the state. So in that case, maybe the simulator has a subcomponent where it uses the model to create a symbolic state from a camera or something like this.
Yes, I think for input, it would be quite interesting. So if you have, for example, the desired state of the system as an image, this maybe could be interesting then to use a deep learning model for it, or for speech recognition.
Yeah, I think maybe then if, let's say we don't have a simulator here, but we would have an actual robotic system or some other environment, connection to the environment here, then this could have various subcomponents, maybe to connect to the sensors, and then actually from the sensors infer the state. And there I could completely see some kind of deep learning component.
It might even be on the side of the goal generation. I mean, it might be something observing the user and generating goals for the robot to satisfy some user needs, or maybe proactively satisfy some user needs, actually.
Yeah, I think actually one connection that we discussed, but it's not visible here, is that normally there might also be a connection between the graphical user interface and the simulator, just to give an idea of the state over here. And in the same way, the goal management probably needs to be connected to some sensor systems. And then in this way, I think we can have this loop that Alessandro mentioned, or this connection, where you take input from the environment for goal management or inference or proactivity components or whatever we decide to put under this component here.
So I think this scenario, this example, has a lot of potential for generating very interesting use cases. So it's, thank you very much for presenting this example.
Thank you for the feedback and everything. And, yeah. Right. Any other questions or comments about this? One thing I was wondering is if we can, I mean, maybe it's just a matter of us designing slightly better interfaces, but since we sort of assumed some sort of domain definition language behind here, like a lot of interfaces actually become, well, first of all, the same here, because it's just, if it's just a string inside, everything will be the same, as Peter mentioned as well. But would there be a way to, for example, trick or but let's say attach some kind of ID to the interface to make it actually different type, even though it looks the same from the data point of view. I'm not sure if this is supported by protobuf, but it could be, for instance, that we regard the message type as well for compatibility and not just the data inside.
I think that is intentionally not the case, because then you cannot connect parts that have the same compatible content but different names.
Yeah.
I think it's the intention that only the content is taken. But you could add a field with a different name and an integer content as a marker. Maybe.
The field name is also considered? No, I don't think so, actually.
Maybe not. Yes. I think you're right. The field name is...
It's only the structure, the types and the number of fields. So I think it could be possible to add marker message types that have different structures, but it's a little...
it feels like a bit of a hack, and normally I would also...
It's like encoding natural numbers only using sets of sets of sets.
Yeah, I'm not convinced that I like the suggestion I made, because it's maybe we should just encourage having better interfaces than just strings for everything.
Maybe that's a good idea. Yeah.
But then for this again, I think then we need also the expressivity, also the support from Acumus to actually be able to have recursive structures in there.
Well, then if you have an idea how it can be improved, then please make a suggestion, and we can create a ticket for it, and maybe not in the course of AI for you, but in a follow-up project, it can be implemented.
There could be something like the probe, only it says distinguish messages by name, not by content. And then only the JavaScript would change how it marks the ports.
Mm-hmm.
But that requires a lot of JavaScript coding in a quite big JavaScript project. So
I think it's better to write better interfaces, but again, then yeah, allowing recursive structures would be, I think, more important in that case, because then, for example, the version of the unified planning framework that is somewhere here. I think now I can drag it because I had to change the interface, but this step here was not possible before, because the input type has recursive. I think actually both, because there was an expression type which is recursive. But yeah, but this one actually has a proper interface. Yeah.
The problem is that the message with 2 strings inside can be a reasonable message type for many purposes, and then suddenly they match. Suddenly the interfaces match.
Yeah, maybe it makes sense to improve the matching algorithm, that only the structure of the basic types, or the names of the basic types, are not important, but the message names of complex types should be distinguished.
Maybe.
Maybe we need to think about it.
Yeah, let's think about it.
But yeah, this is the use case Alessandro and I came up with, and I think if all of this works, then we could do some really nice things for planning and execution as well, because this already contains a lot of things in that regard.
Yeah, it should work.
Cool.
Thank you very much.
If I may add a comment on that, I mean, I'm very glad that we came to this point and that you like it also, and that it seems very, I mean, we can then build very different types of robot controlling architecture or cognitive robotics. That's fine. But I'm surprised and I must say almost disappointed by the fact that we don't really need streaming, the streaming feature to implement that. I mean, I don't know. I thought that this could have been a sort of killing example why streaming is so important for AI architectures, but it's not. So why is streaming so important?
As soon as you want to consume more than one input or produce more than one output for an input, you definitely need streaming. If you just want to do a cycle, then you need to do a lot of programming around the corners to make it happen. And then you need this parallel orchestrator that it is possible to have this cycle. But in the strictest sense, you don't need streaming for that. You will just recall all your RPCs immediately when they stop because they have empty input. So you will emulate streaming by recalling the same message or the same call over and over again. But streaming is the true solution for that. Yeah.
I think also one important thing that you mentioned earlier is that things can run at different frequencies. So you could have a...
Yeah, that is also possible without streaming with the new orchestrator, because the orchestrator has threads for each RPC, and once an RPC terminates and it has an empty input, it's restarted. Or if it doesn't have an empty input, it gets restarted and takes the next possible input. But what is impossible without streaming is creating multiple outputs for one input or creating one output for multiple inputs.
And I think also that the robot environment, which is represented by the simulator, probably will need streaming to interact with ROS, and will probably also have spontaneous messages from sensors.
So in summary, the new orchestrator is a little bit too good.
Yeah, I mean, the people that already did some ROS integration, they don't use streaming because it was not available, but the orchestrator is able to do it because they just restart the RPCs over and over again. If they subscribe and receive a message, the RPC is finished and is started again to wait for the next one. But this is streaming in disguise.
Yeah, so yeah. I had a similar feeling earlier because like all of these things in the end, they end up doing something similar. It's just, it might just be easier with streaming.
Yeah, and the code looks terrible without streaming because you need to do all you can just not iterate over an input, or you cannot yield an output or multiple outputs. You need to leave the function and know where to restart generating output the next time. You can work in Python without for or without yield, but it's not nice to do that. Yeah, that's like streaming.
So let me see if I understand. So in practice, with the current parallel orchestrator, you could very well simulate streaming by saying, well, you just have an RPC call that whenever you receive data, you put it internally in a queue of your component, and then you return. Then you put the next one in an internal queue of the component, and then in the component you just work on this queue and take messages when you want in the order you want.
Yes, exactly. For input and for output, this is possible.
Right. So I mean, seeing like that, streaming seems sort of useful facility because it makes it a little easier to deal with these streams actually without an internal management. But it's definitely, in principle, it's redundant. It doesn't do anything that couldn't be done by just a little bit of more internal programming in a component.
Well, I think it makes a lot of solutions much more easy to really solve. I've seen people doing object-oriented programming in C. That's also possible, but it's really not a very comfortable way to do object orientation. So I think the streaming really makes elegant solutions possible, and also makes it possible to even to think more complex solutions and to find solutions for them.
And the new orchestrator that is too good, it only exists because of streaming, because otherwise, so the streaming was first, and then came the need to create a new orchestrator to cater for all that streaming, the different frequencies. And now it turns out that we don't need the keyword. We don't need the streaming keyword because we have the orchestrator, but we can make our component code much easier to read and easier to write if we use streaming. And we can connect any streaming to non-streaming ports and vice versa. So that it doesn't cost anything to use streaming in that sense. Doesn't reduce flexibility.
It is more effective than doing everything manually.
Yes.
Yeah. Yeah, I mean, as you probably imagine, I'm thinking now also in terms of the paper we were to write, so in terms of extending Acumos to more general AI component or AI architecture. So it seems that the real game changer is the parallel orchestrator, is not the streaming feature.
I have a few more slides that might show such a game changer. I'm not sure, but maybe.
Sorry to be playing the devil's advocate, but we need a strong paper.
Yes, yes. So thank you, Alessandro and Uwe. Now I have a few slides. How can we interface with subcomponents that are reasoners? And yeah, there are many ways, and there is no one fits all solution. The first thing, the straightforward solution, it's what I used for the Sudoku. Solve, input problem, returns answer. Okay, one problem, one answer. It's done. The component can lose all the state. Second possibility, we have a problem and we say how many answers do we want, and we return an answer with a status, a set of answers with a status. We can return 5 answers. So the solver, the reasoner, has to produce all the answers and then sends them back in one package. Not elegant, but possible. If we use streaming, we have the same thing, but we get the first solution as soon as it arrives and can already process it downstreams. So we say, what is the problem and how many answers do I want? And I return a stream. How many answers? And as soon as the first answer is there, the solver can send it out and we can process it. But this is not all. We can do a fine-grained control. We can make one solve call that has a stream of requests and returns a stream of responses. Okay, this should not be a problem. This should be solve request. Yes. So we have one such RPC with stream in, stream out. The solve request can be one of several commands: sending a new problem, changing a problem, computing the next answer, explaining an answer, computing a conflict. I'm thinking here more about logical representations. We probably can do the same with deep learning by changing parameters, changing dropout frequency for training and so on, seeing what happens with that. Masking, like there are networks that you can, where you can mask certain part of the layers to simulate like problems in the brain and see if it can still detect the output, or if you can manipulate it so that it detects the wrong things. So those could be requests in the input stream. And in the output stream, we get answers or explanations or conflicts or a status, depending on what you send in as an input. And so in the deep learning case, this would be classifications or layers or whatever. So you have like an interface, one interface to another component where you can send in commands like in the shell, and you get results which like what is printed by the component. And the important thing is the component has this one RPC, and the state stays in the RPC. If you have multiple RPCs and you stream in on 2 RPCs and stream out on 1 RPC, the state is in the component. You cannot say, I use this component for 2 purposes. This component can be called by several clients for multiple purposes. Would not look nice in Akomos, but it's possible. And there are even other possibilities. If we want the same possibility, but an easier connection to other components. So let's say we have a send problem. We have a component that creates problems. And we have another component that requests answers. Then we cannot use this unless we have a custom collator again. Then we could have a solver that has set problem that just returns a status and compute next answer that returns an answer or an answer with status. Or we could have 10 RPCs for different 5 inputs, 5 different outputs. The advantage of this is we can connect easier to other components without any collator. The disadvantage is the state is in the component. Yeah. For the purpose of AI for experiments, this is perfectly valid because this is about, we can graphically assemble a solution and one component in the design studio, in the canvas, will have one purpose. If we want to reuse that component in another setting where multiple callers might exist, such an interface cannot be used. But here it can be. And if we have this again, we might again stream in things or not stream in things. If we have this interface, we must stream. Otherwise, it doesn't make sense at all. And if we have this interface with one problem and multiple answers, but we want to have the first one as soon as possible because it might take very long to create each subsequent answer, then also we must stream. And those were the last slides. Now there is more time for questions. Thank you for your attention. This would also, so if we don't have any more questions, this would also conclude this workshop. I have no more content, but I think there will be some more discussion.
One question about the collator. I was wondering if the collator is multi-threading capable. So it needs to interface with different models, and the example you showed, the source code, would that also be ready for a multi-threaded setup where the components, the connected, the input components send independently at the same time, sending several messages?
Yes, it is implicitly multi-threaded because the gRPC server that calls these RPC calls, it is a multi-threaded server. So they will all run at the same time, actually. That's why I need a queue. The queue class is multi-threading safe in Python. That's why I also use this queue, because it is safe to access it from multiple threads, and get and put does work in the correct way.
Okay.
But yeah, that's important. It is multi-threaded, and it is also possible to, I also made it in a way that it will consume as much as possible, as fast as possible input, and just discard all the input that is not consumed. So you have a get where you send in to the collator. You push everything into a queue, and if the queue is full, the queue has size 1, you discard the message and write the warning. This way, if the camera is much faster than the YOLO system, you still stay synchronous or approximately synchronous, at most 1 frame wrong in the visualization. Otherwise, the camera image will run ahead of the visualization. I observed this on my system that they were moving apart from each other because one of them was faster than the other one. And the orchestrator orchestrates as fast as possible. It doesn't wait for synchronization anywhere. This is at the moment not intended. This is not planned.
Okay, thank you very much. So I think this collator is a quite important example for general streaming processing.
Yeah, we should have a collator generator that generates the 100 lines of code that are necessary and the Docker file, and maybe builds the image and uploads it somewhere. If you just give it a bunch of protobuf definitions. Yes, it is not a tricky thing, but of course it takes time and nobody has time. So, well, there are many other things that are more important at the moment, but having a collator generator would be interesting.
We should at least create a ticket with all the ideas you have already collected and presented.
Just, I don't know if there's, can I ask a question?
Yes. So
it is regarding the custom collator also, and the synchronization and dropping of messages. So from what I understood in your application or in your implementation, so when we receive a message and the buffer is full, right, we immediately drop it. Wouldn't this lead to some lag? Let's say, like, the message, we received an image and the YOLO takes a long time to process that image in the parallel flow. That's just the problem of the YOLO taking a lot of time. But nevertheless, my question is, how do these parallel flows work when there are like multiple parallel, not just one collator? Would this become a synchronization issue? Because it's what you're saying. We may, if we have like a really big pipeline and we have multiple parallel flows, and we start dropping messages in one place and not dropping on the other parallel flow, how would this synchronize?
It would not synchronize. So the solution that I see at the moment is to drop messages that cannot be processed so that we can try to be as real-time as possible. This is the synchronization that I see at the moment. There are concepts and plans to have message IDs in the input, message IDs in the output. And if this field exists in the protobuf, then the orchestrator will automatically attach the ID of the message in the input into the corresponding field in the message output, that we can see which message was generated from which input message, and also to generate automatically running IDs for everything that is, every message that is created in addition, but this is not implemented yet. And this would allow some kind of synchronization. Also, we don't have a notion of time. We don't have timestamps anywhere at the moment. This can be added, but it needs to be added. It is not in a generic way because it would need to be a field of the message, I think. But in general, if you have multiple parallel streams, it would not synchronize, not by itself.
I ask this because in our orchestrator, we do have message IDs, but the problem is that with those, we can't stream. We can't implement stream because, let's say we streams, what would be the message IDs of the messages that are, because with streams, we can have like one message suddenly divides into 4 or 5 or infinite messages with one stream. So we cannot have that concept of generating an ID that traverses through the graph from the beginning until the end.
But you generate the ID of the image. The YOLO has to copy the ID of the input to the output, and the collator, if it gets a message on one side, it has to wait for the message with the same ID on the other side.
Yes, that works. But the example is, what if YOLO would be streaming? YOLO receives an image with ID, let's say 1, and then he streams multiple replies. What would be the IDs there? It cannot like be 1, 2, 3, because then there will be the next image would have also ID 2, and they would not be unique in that sense. So we would lose there. So
I think it's not, the orchestrator cannot handle this in a general way. It must be implemented in the models. So we had a similar problem when processing audio files that get segmented into many smaller audio segments. And what we did was to add a job ID, which corresponds to the audio file, and then a segment ID, which corresponds to each of the smaller files. And then at the end, there is one component that brings them back in the right order based on the segment ID and the job ID. And it's the components, the models, that generate those IDs. So it's not the orchestrator, because it cannot know how the IDs are in context and how they play together. So I think this is something that the models need to solve themselves, and it needs to be reflected in the messages by stating clearly what are IDs and what are they for.
Okay. Yes, I agree. That was maybe a possible solution, is that we stop dropping messages and the application needs to know when it will need to drop messages. If it is real time, it will drop. If it is not, then it will finish when it finishes. Okay. And I just have another question also, because we are using volumes in some applications. How does that work in Acmus? Is that even possible? Just a general question about volumes.
Well, yes. So there is the concept of the shared folder, which is basically an abstraction. So it can be in our current deployment client, but the Kubernetes client will create persistent volumes, as they are called in Kubernetes. And if there is at some time also a Docker Compose deployer, then this would be then a shared volume, I think, is the name of the concept in Docker. So it's a kind of abstraction, which is independent from the underlying technology, but the idea is to give common storage to all nodes of a pipeline, or at least to the nodes of the pipeline that are connected to the shared folder provider.
Okay, and
I think we have also a small tutorial on the AI for You experiments playlist, which presents the June release of AI for Experiments.
The YouTube playlist.
Yeah, the YouTube playlist. What did I say?
Playlist.
Okay, the YouTube playlist. Okay.
Okay. I'll check it out.
There was also the question that I recently got. Can we have not a persistent volume that is shared, but can we share a local folder with one component or with multiple components for easier development of components? I found that from what I found, there is no universal solution in Kubernetes to share local folders with Kubernetes pods, but I'm not sure that I searched good enough. Maybe Martin, you know about this.
So let me repeat if I understood correctly. We have the use case that for development, the developer wants to access directly a folder inside the pod from the host machine.
Yes, or we run a server of one component from the pod, but the source code is on a shared volume that can be edited in an editor on the host.
Well, the first thing that comes to my mind is that we could add another utility script to the deployment client, the Kubernetes client, which exactly does that, to add a local folder to a pod. I think it's maybe not the best way to do it in the design studio, but locally, because then we have all the necessary access and permissions and so on already at hand.
Mm-hmm.
But it should be possible. I see no blocker.
Okay, with a script, this would. Yeah.
Mm-hmm.
Yes.
Thank you. Great workshop. Very well done.
Thank you very much. See you
Yes.
all.
Great workshop.
Bye.
See you soon. Bye
Thank you
bye.
very much. Bye bye.
Bye bye.
Bye bye.